We are going to kick off our talks today with Alex Matrosov from Cylance. He wrote a book called Rootkits and Bootkits. Is that backwards or forwards? And he's going to talk to us today about subverting the BIOS. I know you've all had lunch, so stay awake and enjoy the talk. Alex.
Hello, everyone. My name is Alex Matrosov, and I will be presenting today Betraying the BIOS, where the guardians of the BIOS failing. So actually, the talk will be focused on some of the technologies which is supposed to protect the firmware, UEFI firmware specifically, and this kind of threats actually always under the radar of normal malicious normal security software and antivirus software. And also, actually, this research being done for Black Hat Vegas this year, specifically for BlueHat, it will be a bit extended. And also, I'm currently actually leading embedded security at NVIDIA, but before of that, I actually been at Cylance as principal security researcher, and this research being done at the Cylance time. Before of that, I actually been a security lead for Intel UEFI firmware security, and yeah, I actually one of the authors of the book Bootkits and Rootkits, Advanced Malware Analysis. So what we are talking about today. So we will start about the attacks on the BIOS updates and how actually the updates for the UEFI firmware is failing, and why is it is failing, and which kind of attacks the attacker can use it for get in without physical access. And after that, I will explain first known Intel BootGuard attack. And it is technology which is actually protect the secure boot from the hardware side. And specifically, I will focus on American Megatrans implementation. And we will talking about how the technology works and where is the sensitive places and how the attacker can actually bypass this technology, and discuss the rules which are used for bypass it. And I will give you details about some BIOS guard implementation too. So BootGuard, it's totally actually undocumented technology, and if you're interested, it will be some details which is actually not published before my talk at Black Hat. And today I will also talk about the tool which is make some validation for the Intel BootGuard. But let's start from the beginning. So why actually the BIOS is a very interesting place for the rootkits? In the past time, actually, rootkit started from ring tree and just load some malicious driver inside the kernel, or abuse some driver objects inside the kernel. And after some time, when the secure boot and code signing policies for kernel mode driver appears, it's before secure boot actually appears, it's been a time for the bootkits, because attackers start thinking how we can actually get in and get a little bit deeper with the system boot flow and attack the MBR master boot record and volume boot record. And okay, but after that, in 2012, the secure boot been introduced, and in nowadays, actually, all the systems came with active secure boot, and it's very, some cases with WannaCry and other malicious threats, it shows ransomware shows it's still a lot of systems which doesn't use the secure boot, right? But it's supposed to be there. And if we're thinking about very complex, sophisticated threats, and it can be BIOS, and specifically for data centers and the clouds, it's very sensitive place. If the attacker came with supply chain attack on the server inside the firmware, it can expose all the guests on the server if it will be no specific protections like memory encryption or something else, right? So very interesting place for the attacker is system management mode, which is currently one of the most privileged modes inside the Intel x86 architecture. And actually, why is the last line showing we're going from system management mode to the operating system level? to rank 0. Because actually, yes, you can parse all the physical memory from there, but if you want to track some specific applications, it's very interesting to be present on the operating system level. And it's actually not difficult to inject some malicious drivers or something else from this level, because you control the memory space, and you can just like modify some of the structures if it will be no integrity checks. And I want to say, actually, as more mitigation we have, as more complexities grows. So currently, all the rootkits, it's going closer and closer to hardware. We have from some like known cases, examples like RK loader from hacking team, or some implants which is being disclosed with Vault 7 leaks. This kind of threats actually can bypass all the modern mitigations if the BIOS doesn't have any protections or deliver unsigned updates, right? So, and this slides actually I copied from the presentation from Intel, which has been presented in this BlueHat, and we can see like a growth of the BIOS incidents, which is actually been involved with Intel PCert. And interesting thing, actually, configurational based issues has a very high rate here when like the platform has the issues and by default configure unsecure way. And it's actually very, very bad when this kind of things happens, because for supply chain attacks, it's a perfect vector, right? And Google introduced the chip, which is Google Titan recently, and it's very interesting case when the company developed something for like armoring root of trust on the hardware side. Because if it doesn't trust the hardware, how we can protect root of trust for the secure boot and other things, and trust like peripheral devices there, right? Somebody just install like PCIe device and then get access to with a DMA attack if it will be like unsecure way, or VTD will be doesn't initialized very early. So it's very interesting case where the company not really related with this like hardware development or related with the end customers, things like pixels, but develop the chip which is actually protects the root of trust. I like this approach, but I also very interested to get one for looking how it can break it. So yeah, let's talk a bit about the BIOS update issues. UEFI firmware, actually it's very huge. UEFI firmware ecosystem is very huge. Now it's automotive, and actually it's not only x86 system, it's a lot of ARM CPUs developers, like companies use UEFI firmware too. And it's like very, very huge world. And some of the companies actually developed some frameworks, like American Megatrends, Insight, and Phoenix. And on top of these frameworks, companies developed their own firmware. And a lot of companies like Gigabyte, Asus Tech, and others doesn't care too much about the security side, because like they're small and they just want to ship product as fast as they can. And it's a lot of like hardware features came always with a new hardware, and they don't have really even like security validation process for their firmwares. And also, now it's no more legacy BIOS on new hardware, but we have legacy inside UEFI firmware. And let's actually look inside the firmware update image how many other firmwares came with a BIOS update image. So actually, just recently, like Infineon case with TPM issue, right? So, and actually, TPM updates sometimes came also with a BIOS update image. And we do have like network adapters, we do have graphics, sensors, embedded controller, even power management. Oh, nowadays actually the batteries has a firmware too inside your laptops. So AMT, SMC, BMC, like a lot of different firmwares. And if like the door, like UEFI firmware update, doesn't have authentication or proper update validation process, it's open door, right, for others to break other levels of firmware. And it's very interesting what kind of things we will discuss today. So we will touch ACMs, a bit management engine, and mostly focus it on the boot guard. So all the vulnerabilities which I will discuss in this talk, it's based on my research on American megatrends, and it will be covered some issues from Gigabyte, Asus Tech, Lenovo, and MSI. So this figure actually shows how many simple protections like lock-in bits we have inside modern hardware from Intel. And some of them is pretty simple. It's just like lock bit for doesn't update or read SPI flash protection, SPI flash, or we have SMM BIOS write protection bit, which doesn't allow from the operating system to get in SMM without disabling this bit, which can be disabled only from SMM by a specific driver. And we have a BIOS lock bit, which is locking the BIOS from the updates. And we have fancy technologies like BIOS guard and boot guard. Boot guard actually armoring the secure boot, making root of trust much more secure and starting earlier than BIOS for validation, the chain of trust. And BIOS guard actually armoring the updates. And both these technologies working with ACMs, which is actually executed in authenticated cache. And specifically for this talk, I actually found some vulnerabilities, which is actually pretty simple. Some of the vendors just don't use the protection bits, and some of the vendors don't use the policies for the SPI flash regions for like isolate some of the regions to be updated or be written from the BIOS update process. And also, some of the vendors just don't use the digital sign for the updates authentication, which is allow attacker modify the BIOS image and deliver something malicious. And some of the vendors like Gigabyte don't use bootguard properly, and it's allow attacker to actually bypass this technology. And I will introduce one of the first known bypasses for this technology today. So how different vendors care about the BIOS security. And you can see here like different vendors. Some of them focus it on enterprise market, some of them on the game industry. And you can see the difference. And also like a lot of people think like Apple is a good example of perfect hardware vendor, which is not actually true, because they also don't use all of the mitigations. And as example, they don't use bootguard, and they just have a secure boot, which is started after the BIOS already like passes the PA stage, platform initialization stage. But I think it will be improved soon because they have very strong security team for UEFI firmware. And on other side, we have a Dell, which is actually being very responsive for my issues, and also like they don't have it too much. And I like how they protect the BIOS update routine with a BIOS guard, because they do it a bit different way, and it was very hard to break it. So, and some of the vendors, it's a screenshot from the tool known as a chipsec, and we can see like don't have any of simple protections on Reds. And actually, this screenshot being done for for 7th generation Skylake from Intel, and the hardware being released in January this year doesn't have any protections, and they just don't care. And specifically on this hardware, on BlueHat Asia, I make a demo with UEFI ransomware. It's pretty simple way, but it's show very in visual way how it can be bypassed. So it's already released in my other talk, the details. But if we go some specific exploitation flow, so BIOS log being not enabled, and attacker is able to modify BIOS write protection bit. So and we, as a hacker, we can arbitrarily write to the spy flash chip and make it persistent from the operating system level. So specifically, this demo show us we have a docx document which is drop some infected UEFI firmware image on the file system, and then sign a driver from American Megatrends being update, using this update to deliver malicious firmware without any modifications inside the driver, but I use a privilege escalation in this driver. So, and don't verify the signature and deliver the malicious update. It's not a rocket science, and it shows actually it's possible ways for remote attacks on a lot of different firmwares. And the main root of actually also a problem. Not a lot of people really update the BIOSes, even the companies. It's hard, right? So we have a zoo from different vendors and different hardware. And it's hard to control how many hardware have recent update, which is or how many doesn't have it. So, and from attacker perspective, if some malicious, if malware came on the operating system level, it can actually try to check how the firmware is up to date, or check for known issues and try to actually attack it. So, how many people update the BIOS in this room? Okay. That's good to know how many people not updated. This picture actually shows the flow, how from the operating system level we can get in spy flash persistently. And thing is like we need, of course, I don't know, memory corruption or some bug inside browser or flash or whatever. We just came up through there, or spread phishing email with a docx or PDF. Then, of course, we need to get into the kernel mode, because without kernel mode, we can't communicate with the SMI handlers or some of the services which is responsible for the BIOS update or writing to the spy flash. So after that, we map it or use a specific application from the vendor to map the update image for some specific memory region. And after that, we call inside the system management mode the service, which is actually named as SMI handler, to get this image, read inside the SMM, and update the spy flash. Or it can be actually done in different way, but some of vendors which I checked doing that way. So, and even if the drivers, even if BIOS update is signed, if any vulnerabilities inside this SMI flash or SMI handlers, which is, if speaking, simply explain it, it's like callback function from BIOS to operating system level for reading and writing the spy flash. And in the past, a lot of them used just SMI flash driver, which doesn't authenticate update. And it's been like a lot of issues there. And after some time, some of the vendors start using security SMI flash, which is validate digital sign for the BIOS updates. And actually, I found one issue on ASUSTeK with this SecSMI flash driver. And even if BIOS sign it, you can attack SecSMI flash to modify the flow for the flashing update without any sign verification. Here is a bit about the semi-flash issues. So this specific driver are responsible for writing, reading, and like enabling this kind of function. And also, it is like getting some information about how SPI flash, how many memory it has, and how actually BIOS update feed for this. SecSMI flash, it's a bit more interesting because it's validate the update for digital sign, and it's load image and get information about sign and validate the sign. And actually, here is the number of SMI handlers, which can code from the operating system level, and all of them being vulnerable for simple callout attacks, which is pretty much simple to exploit, and what I did. And of course, it's why BIOS Guard been created by Intel. And actually, BIOS Guard, it's pretty interesting technology, and it's available on most of the platforms which is used at vPro. So it's a bit about responsible disclosure fun. So, and you can see how much time you need to patch the issues for the BIOS, even if it will be like one bit change inside the BIOS code. But most interesting part, it's like how some of the vendors react. So I submit the issues to ASUSTeK, and after a month of my email, they send me, I send a follow-up email, and they say, okay, it's no issues. I say, how come? Actually, I found the issues, I send details. No, we patched it already. So I make a bin diff of BIOS update, and then I see like they patched exactly my issues in new update just like few weeks after I send it email. And after some pressure to ASUSTeK, they actually send me another email where they say, okay, yeah, we recognize it was your issues. And it's also like shows the level of the vendors, how they ready to communicate with researchers and research community, which is actually without any money tried to help to fix and try to actually make their products more secure, right? It's no bug bounties from ASUS. It's like we just giving them for free. And if we switch on the mitigation technology, I want to talk about the Intel Boot Guard, which is pretty interesting technology. It starts validate chain of trust from early beginning, even before the BIOS started, and it's actually very good from the security perspective. But it's also like always, some of the things come for the manufacturing and third parties implementation, I mean like hardware vendors and IBVs. And it's where they failed, but let's talk a bit about different shades of secure boot. Original secure boot been introduced in 2012, and actually root of trust been fully based on the BIOS. That means any issue inside the system management mode, or not only sometimes, can break it root of trust. So, or attack surface based on firmware there. After some time, it's been introduced at measured boot and verified boot schemes. And measured boot is actually based on TPM, where the root of trust is TPM. But all the secrets and all the code implementation stored inside BIOS. So, and it's still attack surface will be in firmware, right? And only verified boot has some field programming fuse hash value, which is log root of trust inside the hardware. And here is firmware and hardware attack surface came. So let's talk a bit why bootguard has been created. So classical secure boot starts from the Dixie phase, which is most recent phase just before firmware passes the control to the operating system bootloaders. And it can be impacted with any SMM issues or like SMM or BIOS implants. Not all of the BIOS implants, but from SMM BIOS implants, definitely. And also, it was no verification for early boot stages like SEC and platform initialization boot phases. From other side, measured boot starts just before pay phase, which is platform initialization, and can be also impacted with the same issues. And as we said before, the root of trust moved with the verified boot to the hardware, and it's how actually Intel BootGuard protect in more like stricted mode the chain of trust. And also for most strongest protection, verification should rely on microcode authentication. As example, microcode is authenticate ACMs for being executed. This picture I copied from Vincent Zimmer's blog, and it's actually first picture which shows some details about BootGuard technology. But it's no open specification, and it's actually a pretty old picture. And I start actually my research from here and start figuring out how actually BootGuard flow works. And this picture actually demonstrates some high-level overview how it's started. So we have a CPU reset, which is pass control to the CPU microcode, and authenticate ACM and load from BIOS update image. Actually, ACM stored in BIOS update image. And if authentication from microcode fails, attacker just can use some malicious or modified ACMs. And ACM verifies the flow after that and pass the control to reset vector. And IBB, which is initial boot block, it's some hashes values, which is verifying second the pay phase, and after that just pass the control to the classical secure boot, and operating system will be loaded. Intel BootGuard technology has a few different operating modes, and most strongest mode is verified boot when the root of trust, as I say, located in the hardware. And you can also use in the both modes, like measured boot plus verified boot, which is most strongest mode for the Intel BootGuard. This picture I also copied from Vincent Zimmer's blog post. And let's look how actually policy verification works. So on the different phases, we have a different policy. And I start figuring out how it really works. So, and the start point, it's actually field programming fuse. After that, we do have like IBB, which is initial boot block, and ICM actually verify IBB. And this picture actually demonstrates, in my opinion, like real-world picture, at least for some of the BIOS vendors. As I say on beginning, I reconstructed American Megatrends BIOS, and it probably looks very close as it is in standard. So, and all this being extracted by reverse engineering. So we have a K manifest, which is store hash of IBB public key, and OEM root public key, and actually OEM root public key should be logged by field programming fuse. If it is not, actually it can be an issue, but it's not enough. I will say why a little bit later on my slides. And this kind of policy is stored inside the BIOS update image. So any attacker has access to the BIOS update image. It's mean like he can download from the vendor side and play it on top of it a bit. So only this part rely on the hardware. All this part actually stored inside the firmware. And it's actually, this picture demonstrates the root of trust. And this been specifically released before my talk on BlueHat by Dell. And it's most actually detailed information about how bootguard works from some of the vendor which has access to the documentation. Yeah, and it's actually same thing, but relying on Dell documentation, which is we seen before. And I actually checked different vendors' configuration for the boot guard and BIOS guard. And we can see how different it is for different vendors. And some of them using the boot guard, but don't use the BIOS guard, which is actually make BIOS update process much more unsecure. And most actually worst ones, it's Gigabyte, MSI, and Asus Tech. But also some of the vendors like Lenovo on some of the platforms don't use at all the boot guard, but so it's possible because it should cost some money, right? For more expensive systems they do. But this kind of systems I a bit research for my talk. So as you can see, trust no one, because if you see on some information, feature information on the website, they use something or not, it's just say they have this technology in your hardware, but how properly they use, you don't know really. And for specifically for preventing supply chain attacks, it's very important to actually make some validation process for the hardware before it will be shipped to the data centers. First information about the boot guard came from Alex Yermolov on last year's Zero Night talk. And it's interesting because he found the system from Gigabyte, which has the boot guard, but the boot guard not been enabled and not been actually configured. So if attacker know how modify this technology in active stage and then deliver malicious update, actually attacker can just log the rootkit inside your firmware, and because the attacker has a private key for all the policies, and it will be logged by field programming fuse, it's no way how you can update or extract this rootkit. So it will be locked forever. It just needs like a lot of, probably it's, you just provide this to trash the hardware. So it's how it looks in policies inside feed tool, Intel Flash Image tool. And you can see like boot guard doesn't enable it, and OEM public hash key is zeros. So, and also in this case, field programming fuse not been set up. So that's mean like attacker modifies the public hash key, delivers a malicious update, and logs the fuse. So, but here BIOS boot guard not been enabled. It's not bypass. It's just like Alex used boot guard for enabling the boot guard and show how the rootkit can be logged inside the platform as a POC. But as somebody on Twitter says, you never attack the standard, you always attack, you always attack implementation. And I actually get to look inside how specific platforms works for validate the BIOS as a boot guard. And as we can see, like K-manifest, and it's stored in the UEFI firmware image. I reconstruct some of the fields from this structure, and we can see here is a public key, and if root of trust not locked in the hardware, attacker just can change all the keys, right? So modify all the policies if he knows where stored what. And we do have IBBM hash, which is also need to be changed for the attack on the boot guard. But I will discuss all the flow a bit later. Also, I reconstruct initial block boot manifest. It is here. So we have IBB hashes, which is actually validate second PA phase, and IBB offsets, which shows where is specifically located protected regions inside the UEFI BIOS. So, and also we have a RSA signature, which can be changed, and public key, of course, too. So, UEFI tool some time ago already shows and parse in the feed boot guard policy and K-manifest policy, and also shows where the ACM stored, so you can easily extract that. It's because in EDK we have values for the feed structure, which shows where it's based offset for these specific policies. And it's actually how initial boot block looks like. So we have hash, value, and offset. So, and it's example specifically for this IBB, which is a window covered by these hashes. And also, if the vendor make a mistake on the covering the BIOS update with the IBB hashes, so it can be some window which is being unprotected, and attacker can use it for modifying that. If it will be like executable code, it's like the flow for delivering some rootkit. Also interesting part, it's Authenticated Code Module, which is all the ACMs, which is I seen before, like it's shipped by Intel, and it has some header, which is actually pointing to entry point inside the ACM module, and the ACM module actually executes in the hash, in the cache. And we do have a digital sign for each ACM module, and it's actually will be verified by microcode. So what kind of things, actually what kind of parameters for ACM we have? So it's x86 code, specifically 32-bit. Executes in ACRAM, which is kind of cache as RAM, also known as non-invicted mode. And it's all the ACMs, it's CPU and chipset specific, so it's because microcode validates the sign, so if your CPU generation doesn't have verification for your ACM, it will be not executed. And ACM verifies the key manifest and IBBM policy. I start thinking about like, okay, we have executable code inside ACMs, and I reconstruct some format and build some loader, simple loader for IDA. But most interesting thing, it's like how if we bin diff different generation of of ACMs, ACMs for different generation of CPUs, how it will be looks like for one technology like a boot guard, right? So, and actually ACM code is pretty complex. We have a flow, even like we have some crypto verifications there for SHA-256, RSA, and everything is there, right? So, and it's pretty complex technologies. So it's flow from ACM, but most interesting part is I make some bin diff with different generation of CPUs. So Haswell versus Skylake, and I doesn't found too much here. I don't know, maybe I've been just unlucky, but I found really small change. But when I did some bin diff with Broadwell versus Skylake, I found like a lot of changes, and these changes show me like this kind of parsers has a lot of issues, like some of them integer overflows, some of them really like mistakes in the code or whatever, but it's a lot of patches been there. So, and let's talk a bit how many components BIOS guard has inside the BIOS. So we do have a platform initialization module like boot guard pay, SMM, which is actually verify firmware boot guard from SMM when it will be like not fully rebooted. The hardware will be not fully rebooted, and it's just like warm reset. And Dixie, which is verify the boot guard from S3 sleep mode. Here is a flow for the pay validation. And we can see here, actually, in this flow, it calculates the hash, and it stores the hash. But we also have a flag, which is 0 or 1 in specific case, and it shows it's validated or not, and it's passing to bootguard Dixie driver. So, and it's actually validate pay firmware hash, which is covered all the firmware in my case. And what happens actually? How verified boot guard from SMM validation flow works? It's find and verify ACM and verify all the keys. I will be a bit speed up because I have just 7 minutes, I think. So most interesting thing in this slide. As I say, it set a flag for 0 to 1, true or false, when the validation is right. And here is actually, yeah, I show this issue on BlueHat. Now it's already fixed on mostly on all the vendors, and it's been fun because some of the vendors from like huge enterprises came to me and say, "Oh, we just recently patched it," and I don't have a time to really like follow all process to disclose this issue, and it's small bug actually. Thing is, this logical bug opens the door when you have like S3 reset to put some malicious components or code inside your BIOS, and bootguard doesn't help here. And actually, Embedded as a company recently, based on top of my research, released same thing to Intel NUC, and it's already patched. And they do have some blog post, which is a bit provide more detail about how they exploit it. Here is my target platform, and it's 6th generation core on Skylake. BIOS guard is enabled, and boot guard is enabled. BIOS guard is not. Here is vulnerabilities. Both, as we can see, it's for bypassing the boot guard, it's need 2 vulnerabilities. First, it's read access to IME, and second one, the configuration for the boot guard is not locked. Why we need vulnerability for IME? Because we need to lock the fuse, and the fuse can be locked only from IME. So here is the details from Intel ME tool. So on this platform, as we can see, FPF doesn't set, but the public key from IAM is in place, and verified boot and measured boot is enabled. But also we can see like ME region has access for read and write. So here it shows like we have most strong mode for boot guard enabled. And the funny fact, from Gigabyte official website, they propose this hardware for like governmental, for critical infrastructure, for hospitals. But don't care too much about the security. And here is a flow which shows how the boot guard can be bypassed. So we actually, because we control all the structures or the policies inside the firmware, we just modify all the things like, and that's it. And if it's not locked in the hardware, so we just actually can bypass all the boot guard policies. So here is the Intel statement, and Intel says like third parties IBVs should actually lock the boot guard root of trust inside the hardware, and it's probably written in the specification too. So it's a Gigabyte statement, which is say like they released the update, but the update should be separately from the BIOS update, download from the website of vendor and installed. And I don't know how many users will do that, right? This month, actually last month, I developed UEFI tool update for Intel boot guard visual verification. And it shows specifically how many firmware volumes and what kind of drivers is covered. Here is a blog post, here is a link to the tool. And specifically for BlueHat, this Sunday I pushed the update for UEFI tool, and now it supports Surface laptops too. And actually, I've been surprised, and on Surface, they did a bit in-house implementation of Intel boot guard technology, and it's much better than others vendors. Not all of the others, but a lot of the other vendors. So here is a link on my Black Hat research, and actually I will be update after 0 nights with all my templates for 01 editor and all the scripts for IDA. Thank you very much for your attention, and if you have any questions, I will be happy to answer, and I hope we have the time. Yeah, we do have 3 minutes.
Okay, microphone runners will be ready to take your questions. Make them interesting. Or not, I'm not your boss.
Hi. I noticed that you mentioned that only some of the regions of BIOS are protected behind the RSA signatures. Why not sign the entire image instead?
So they sign, so actually, not like that. The signature protect IBB, which contains the hashes. And as you can see, like hashes is signed, and you can't modify the hashes. And hashes actually cover it, all the BIOS usually, but it cannot. So.
What is the reason for like even allowing mechanism
make more flexible the technology for third parties?
So that they don't have to go through hassles of signing every release of BIOS, or what?
As example, they can sign different pieces of the image, different ways, example, or one vendor control sign of one piece and another from another piece of image.
Thank you.
I don't know. It's my opinion, but I'm not a hardware developer, manufacturer. And actually, technology is undocumented. It's just guess. I can be wrong. No more questions?
Just a simple one. When's the book going to be completed?
Excuse me, can you repeat, please?
When's the book gonna be ready?
Boot?
The book.
Book? Oh, soon. Actually, we made some early release for the DEF CON, and it's been sold out. So all the book, it's already ready. Early access will be updated this month for all the chapters and printed in January.
Sorry. Have you guys considered including anything about grayfish?
We don't have, so we already extend like a lot of chapters for the BIOS, and we have a pressure from publisher to not add anything more. So probably next book will be like open wiki book, because it will be easier to add more and more content and don't have logistics with publisher, right?
So in a perfect world, if you got to decide exactly how the disclosure process went with the vendors, what would be your perfect version?
You know, like it's difficult, because perfect world for the vendor, it's one world. Perfect world for researcher. I am both sides, right? So it's difficult, actually. I think like, at least I expect some collaboration from the vendor side, because like if you send something, then like send follow-up email, and the vendor like reply no bugs, but then release the update silently with your bugs patched. It's a bad way, right? So here is like some should be best practices exist, right, for that. Like be polite with researcher. And researcher will be polite with the vendor. So, because like in the UEFI world, it's not a lot of bug bounties. Actually, Intel offer one, but it's covered only their products and their CPUs. It's also included the hardware bugs for UEFI firmware. It's just for the NUCs and the servers. So it's not a lot. So probably Microsoft will be introduced some bug bounty for Surface. I don't know. Thank you. One more question here.
Just out of curiosity, you mentioned that vendors have a lot, like obviously have bugs, and then you asked us who updated our BIOS recently. So the question is, just again out of curiosity, is there any common techniques or procedures to basically push the pressure on customer to update BIOS, or how it's done in hardware?
You can't push the customers, right? And what you reply, you update your BIOS or not? Okay, I'm kidding. So actually, it's no pressure to customers, because it's like, okay, probably if updates, as example for Windows software, will be delivered by Windows update process, it will be perfect world. But it's like this perfect world will be never happens, because like from the vendor, they should prepare the update for specific time frame, right, to be delivered. And also it should be like unified process to update the systems. And this also will be never happens, because all the vendors have some in-house features which is very specific for their hardware. So, and I don't know, actually for the big companies, it's important, and specifically also for the data centers, it's important to probably have some process, at least make some health checks for their hardware of BIOS is what I think.
But it's basically like, you know, on customer itself.
Yes.
To be able to follow. Okay.
No unified solution here. And it will be never happens, actually, what I think.
Okay, so unfortunately, we do have to end questions for Alex because we have the next set. So round of applause for Alex.
Thank you very much.